Now today, the main topic of webinar is query scheduling optimizations and smart query monitoring through AI. We are already doing CADE and QSO, long thing. The new thing is added is the smart query monitoring through AI. So the major 7 points is covering. This is first is the general idea. Second is a brief introduction about the CADE, computer-aided deposit operations. Then after that, query scheduling optimizations. Then after that, we are comparing large flow data with the borehole data to give predictive and actual quality analysis. And then again modifying the model. And then based on that model, we are monitoring the query with respect to quality to support the plant requirement. And then what is the benefit or cost we are getting. So this limestone, which is the major raw material for the cement industry, the three things are there which is unique for the limestone for cement industry. First is that it is a non-renewable resources. So when the limestone is used, we have to use judiciously. Otherwise, we will waste the limestone and we cannot renew it. So we have to use it judiciously, and it is given by the nature. So how best we can use for the cement plant, that we have to look at. The second thing is that we require a specific quality requirement in terms of LSF, SR, AR, or other minor radicals, whatever sensitive radicals is there. This is the unique thing which is different from the other raw material of like other minerals, bauxites, iron, etc. Because all are dependent upon the cutoff, but this is based on the ratio of LSF, AR, and AR. And third is we require a strategic planning to blend different grade of materials, and the plant requires a material consistent quality with minimum deviations, because if the deviation is high, plant will stop or it will malfunctioning and it will create problems. So these three things are unique for the cement industry. Now I'm just giving a brief idea, because these steps we have to follow for the AI to be implemented. Before these basic things, we cannot implement the AI in the supply of material to the plant. The first is the site identifications. Then after solutions, we recognize surveys thing, and then we find out the potential area. Now, after potential area, we go for a first general investigations, so that we can further narrow down the area to which is more potential, and then go for the detailed investigations. When we do the detailed investigations, then we computerized all the data to make a block model. When our inventory is generated, then we give the repository optimization. That means whatever the plant is required based on the main three parameters, LSF, SRER, and other constraints. Somewhere is alkali, somewhere is sulfur, somewhere is chloride, somewhere is MgO, somewhere is iron. So this is optimized on that parameters. After optimizations, we then plan a schedule for a long terms and for a short terms and for daily also. So for the long terms, generally we refer to the 1 year, 5 years, like that. Short term, we refer to the 6 monthly, like that. After that, we go for a comparing the actual versus blast hole data. So because what happens is that when we do the drilling is normally is a wide space drilling. And second step is that the core is very clean. So what we get through the borehole data and what we get in the quality in the actual blasting or in the mines to the run of mines is different. So we just compare these two data, and then we predict this. Okay, this has to be modified as per the model. And after that, this process is coming is the daily online monitoring. We can through AI, in which I will discuss it later in a next slides. So this is just a flow for this to be carried out before the implementation of AI. That once the data is generated, Then we make a cross sections, geological model, then digital modeling, then analysis by statistical and geostatistical to find out which is the best suitable data which should consider for the further processing of the model. Then we prepare the block modeling. After preparing the block model, then we go for the resource assessment. And that we also go with it grade analysis, means at different cutoff grade, what is the quality is there. And then we come out with the maneuver reserves. Now, it has been observed that the grid drainage relations cannot provide the desired quality what we require by the plant. So we go with the plant parameters based on SF, SM, silica modulus, and alumina modulus, and other sensitivity materials. So in that we go with optimization. Then we find out, okay, this is further use material which is further narrow down our area, and with this we can say that which is the reject material and which is the usable material, or which is the blendable material. And then we find out there are many plants running in a particular LSF, SR, and AR. But what happens is that when we do the study, we suggest that what is the best optimum, because we are analyzing now the complete borehole, a complete area of the deposit. So we suggest that if we follow this parameter, then your results will be more. So then we go for the suggestions and go for the global optimization. After global optimizations, this is the table work we do. But when we come to the field, it is observed, as I have told, that there is a difference, variations between the block data and the borehole data. So we compare blast hole data with the block model data, and then again further modify, fine tune the block model. And after that, when our blast hole data is available, further from the blasting to the pile formations is still there is a deviations. These deviations we reduce by AI method, which we will discuss in subsequent slides. So this is just the methodology. We are just showing this after CADE, computer model, when data is generated from the block model, that model we will use for our optimization purpose. After optimizations, we go further. So the optimizations, it is based on mainly the raw mix parameters, and this we go for a long-term optimizations, then quarterly, then monthly, then from parallelly we have a blast hole data. So that blast hole data we again further modify the model, fine tune the model, and then we go for a weekly planning, alternate planning, like that. And all this data which generated is coming to the software on feedback data. And this feedback data is used again to revise the model, and as well as revise the weekly and monthly and daily schedule. And there are many parameters which is considered is that mining constraint, there's and raw mix ROM parameters, the availability of mining equipments, and equipment scheduling. So this is just a methodology we adopt before the AI. This software, the assessment of this material, assessment of the model or QSO is governed by the many softwares. So for block model, we have a SERPAC datamine, then we have a geostat software, then we have a optimization software is query scheduling, then we have one more Ethos GeoBlend, which is also doing the same like a query scheduling, but with some more graphic capabilities and with more huge data volume working. And then again, when we have a blast hole data, we again go to the block model revision with this again geostat and SERPAC planner. After that, we go for a planner, Ethos Geo Planner and Quarry Master. We have this also software, and then we go for our AI-enabled blend optimizer, which does on the blast hole data. And in the bottom, it's in block model. We require first mineral database, then minerals, which gives us a different pit designing and concept of different cutoffs and various parameters, analysis parameters. Then we after optimizations, we mark the what should be the pit after optimizations, because in CADE we have a pit, but that includes rejects also, which we don't know. We don't want to use which is not required to be mined. So this after optimization we do that. And after optimizations, we make a conceptual plan for a long terms, which is further divided into short terms. Then again, this feedback data is being used to modify the block model, and then we go for the query monitoring. Uh, After doing the CADE, we have a concept what our query is there, what our resources are there, what our resources are there. So it makes a concept. So this optimal scheduling of non-renewable resources, which is limestone is non-renewable resources, we do for this query. Then we come to the regular and continuous updation of the deposit inventory on short-term basis. And this also provides the steady supply of homogeneous material. After followed by use of real-time data analysis and advanced analysis, which is the blast hole data analysis. After that, we come to the management of the query. So one of the good thing is that when we know, mines person knows what we have, and the plant person knows what we have. So the difference of opinion between the mines and plant, they see, okay, this is the material available in the mines, and now we have to manage with this. There is always contradiction between the mines and personal principles. If we have everything what we have, and plant people also knows what we have, so they also come to the same page or same line that okay, we cannot do anything in the mines. Whatever the mines can provide, that is available to us. And now what we can do for the plant person, that they have to decide. So this gives the smooth run of mines quality and stable clinker productions and maximum productions with minimum production cost. Moreover, it is environment friendly. Like that, we have a alkalis, or we have a chlorides, we have a sulfur. So these issues we can control, that how much we can reduce the emissions. If it is it can be reduced, then or blended, then it will be helpful for environmental point of view. Then the coordination between mines and plant. Now everything is clear in the mind of mines person and the plant person. Mines knows what I can give or I am giving, and plant also knows what I can receive, and we cannot go for a other material, because normally plant people want a comfortable, that we want a high grade material. So now they are clear, and same thing is helpful for the management also, and this is also good for the company owner also. Then the decision making. After that, we go for the optimized query operations with quality control from the source and minimizing waste. So we can make a decisions which is the blocks which is good, and or which place is good, and which place we can blend it, and how we can minimize the wasting. Then we have a awareness, and awareness with maximum query lifetime. We can increase the reserves lifetime increases by judicial blending. Now, we are coming to the points how to reduce the standard deviations. One, we prepare a traditional model, which from the geological plan or geological sections like that. Then we have a broad assessment of the quality. Then we make a computerized model. Then we have a block wise, we have a assessment. So we further fine tune the quality assessment. Then we go for the optimized block model. So with optimizations is further reduces, because it removes reject blocks, and which is the best block which can optimize from considering the plant parameter. And after that, when we have a blast hole data, we again fine tune the model based on the available informations from the online belt analyzer also, that also we can use. Then after that, our predictive model is ready. Then we go for a AI, because when we have a blast hole data, still from blast hole data to reach the stacker, still there is variation is there. So whatever the material is passing through the belt, that is being analyzed, and then again it is correlated with the blast hole data, and whatever be the blast quantity is available, it changes with through I. So percentage also automatically changes online as soon as the pile is forming. This percentage will be changing from face to face. That how much we have to material, again further fine tune it. And when you go to the raw mill, that and after the correctives, again the standard deviation becomes low, and then the kill field. So our objective is that how to reduce the standard deviations from, suppose when it is coming from the initial assessments to the kill fit to the plus minus 0.1, because the plant people wants, okay, you supply the material of desired quality but with a minimum standard deviation. So that is the main objectives of the assessment. Now, while doing these things, there are many factors which again coming changes. So this also AI take into the considerations, like change in the quality of the limestone, because what we are predicting and what we are blasting, there is still change. Change in the availability of sometimes mining equipments, and change in the fuel types also. Some AFR, sometimes pet coke, sometimes coal, Indian coal, foreign coals, imported coals, and then the availability of correctives. Sometimes laterite is available, sometimes iron is available, sometimes clay. So these are the dynamic scenario. So this dynamic scenario also this take into considerations. This we gives in the data, so that based on that it moves. Now the why we require the remote query monitoring? That is the obvious case is the, this is the cost-effective solution in dynamically optimized mine operations. The first is that we have an inaccuracy caused by wider grid spacings, because wide spacing drilling is there. So we have a much more inaccuracy. An unexpected occurrence of detritus materials. Sometimes material is going on, but we find some clay materials, some heterogeneous materials. So this is unexpected. In the geology, we find that. And then changes in the environmental status, and then the quality variations in input materials, and change in the product requirement by the plant peoples, because some plant is making for OPC, for PPC, for oil well, like that there's plant requirement, it has to be changes. Then we require a ease of mining considerations of the manager. We also help that mines manager should be more ease to supply the material. And then there's also local problem is there, inadequacy of local expertise, manpowers, analytical tools. And one more thing is that operation and maintenance contract. When we give the asphalt maintenance contracts, normally contractors go for a high grade or like that, which reduces the resource conservations. So these all are the factors. That's why we go for a remote query monitoring. What does remote query monitoring achieve? The first thing is that with monitoring of mining operations on a dynamic basis, that is weekly, fortnightly, monthly, daily, pile-wise. Then it allows the flexibility in mining operations by dynamically optimized extraction plans. We have a plan, but sometimes it has to be changed some because of the mining equipments, mining because of the quality, what we have predicted, or some local issues. Then with the assured steady supply of homogenized materials to meet changing quality requirement. Now we have to meet the requirement of homogenized material with the minimum standard deviations for the plant people. Then minimize the human dependency and biasness. And of course, when we follow all these management tools, we have a saving in mining operations. And more importantly is that if have a consistent quality, our deposit life will be increase, and it comes the cost of the mines, and it save the revenue. Now, what strategies we adopt? What strategy we have to do is that in the query monitoring, we have required a specific desired scheduling with the long terms as well as short terms both. And then we have a measurable mining cost, means how much is the overburden handling cost over there, equipment cost is there, that we can measure. Then what are the other alternative approaches there? Suppose one thing is fail, or some material is keeping up low, coming abnormally different quality, then we can have an alternative arrangement. Immediately we have a database, everything is ready, and we can immediately change the approach. And we have to meet the requirement of run-of mines and the raw mix. Both together can be taken into consideration. And the time management is required because we have to prepare a pile within the time frame. So this time management is required to achieve desired goal, like pile formations, weekly, month, or whatever is required as per the plant. The system which require for all this query monitoring is that this internet connection is there, but it remote expert is also required all the data from basic data to the end data, from block model data, global optimized data, long-term scheduling data, short-term scheduling data, equipment scheduling. Equipment is optional because in the cement plant, we have give the more emphasis on the quality because we have to meet the standard minimum standard deviations. So first we give the quality, and then after that we go for the equipment scheduling. Then branch code data, which is has to be modified. Then based on that, we have go for the mine layout, and then query monitoring. And after that, all the data site is incorporated in the system, and the data of blast hole that is incorporated through desktop as well as mobile also. You don't need to go for desktop. You even in a mobile you can enter the blast hole data and you will find the solutions. Now, what is the what is predictive quality assurance? Means we are predicting what we are going to the next. This blast hole data, what is available, this helps us in the next phase or next advancement of the mining phase, what we are expecting to get. So this gives a concept. So what is the evaluations? Reliable predict the quality of the crusher, prevalent inputs. Both long and short-term model would be revalidated. Then comparison of mine blocks with the pre-blending samples. Initially, all blast hole samples would need to be analyzed and incorporated. Then deviation within the acceptable limits, those data we will take which is within the acceptable limits as a feedback. If some data is enormous, this has to be discarded. What benefit we are getting is that increase the usable reserves and the steady supply of homogeneous material to for the raw mix kiln feed. And this results in the minimize usable mining cost, mix cost, and consistency of product quality. And further is that this is reduce the operational problems, which is the more problems for the mining people and as well as the plant peoples. So typical buyback period for this activities normally takes 6 to 12 months for operations cost for total predictive quality assurance. And it is less than the cost of the correctives, etc., saved on a daily basis. Now, this is the just I'm showing the block model updations, how we do the block model, which we have prepared is predicted. Then we analyze, there's different models. This AI takes different types of models and it takes which is this best suitable model for that particular deviations. So it analyzes that. And then we update the model. After that, we send it to the pile. And when the material is being supplied to the pile, formation of the pile, even if the pile is half prepared, still it make a corrections that, okay, you can change the area or change your locations from where further material has to be modified online. So this is just a format for this online. We have a given a data of samples, how much run it has run, what is our requirement, raw mix or raw ROM, how much the quantity is required, what is the LSF, what is the silica ratio, molar ratio, and what is the raw mix. We have a here I have shown only the 5 blast hole data, but we have a number of blood data. We can add any number of data and it automatically calculate what is the ROM is correct and what is the raw mix is coming. In the right hand side, we have given this is the our parameters, and this is the when we bottom we predict it, it gives how much is the data from which blast we have to take and what percentage we have to take. And bottom is the chemistry we have already added. So it is a continuous monitoring, and as well as soon as our pile parameter is changing, it automatically the percentage of the blast also changes so that you can monitor and you can supply the material accordingly till the pile formations. Now, I am just going through the how it works the optimizations through AI. So AI enabled blend optimizer is that it is all are driven mine selections and corrective added dosing for target LSM, LSF, SM, AM, or any specific criticals which is sensitive to the deposit for raw material optimizations. Like LSF, we have a 98, silica metal 2.2 target is. So our source is presently I have shown these. We have a 5 phases open. and we have a three actives. Then AI algorithm is being applied to meet the requirement. It gives us the output and then blend chemistry. And modally, what LSF SM is achieved, that is predicts. And scenario, it gives the scenario that what is the quality mode. There's a two types of things that there. What are the quality mode and what is the cost mode? First priority is given to the quality mode, then we go to the cost mode of from the mining equipment pivot, transportation of material to that, and then pile mode to the raw mix mode. And after that is the sensitivity analysis for mine chemistry, availability of analysis, which is more sensitive from the chemical point of view. Then blend optimizer, after incorporating all this data, what we have and what we need. So we have a blast hole data, we have additive data, we have a constraint that this is the availability of material available at the face. And sometimes we had to remove some material forcefully. So this is the minimum material we have to use from that particular force. And then after that, it coming is the what is the mining cost of transportation to the plant. So in the right hand side, we have a blend optimizer. We have cases in which different percentage of material is being supplied from the mines to the plant and what are the correctives being used. Now we have a optimizer output. So we have already given the optimizer, which is a LSF, silica modulus, aluminum modulus, and it also calculate what is the predictive clinker quality. We also give in this coal quality in the behind. So with the presently, whatever the material is going on, we can still predict the clinker quality which is expected if we change the parameter here. And in this optimizer mine and additive allocations, we can see the material on the left hand side. Second row, second column is that how much is percentage of material being used and what is the tonnage in the terms of per day or per pile or whatever the other, and what is the blend chemistry it is showing. So has been observed, however, it is theoretically observed that there is a advantage in quality prediction in terms of CO, SI2, L2, FE3 from traditional method to AI model method. So CO has more better predictions, as silica is predictions, alumina is, iron is there. Now this slide is that in which we have add quality as with the cost. Means suppose we meet the quality, then we know how much the transportation cost, mining cost is from the different phases or different mines, or is there's suppose more than one mines, different locations. Some mines are 10 kilometers, sometimes some mines are 2 kilometers, sometimes are 30 kilometers. So what cost that are being controlled? So with this we can know how much is the cost if we go reduce the cost. So first is the quality, and if we can meet the quality, what is the best transportation cost or mining cost. So there's a further fine tuning of the materials to be supplied to the crusher, pre-blending or the plant. So now this whole systems, it takes times. The system achieves and implemented. This first is the data foundations. In this, all the blast hole data, XRF data is which considers mine block chemistry is taking, and all the historical pre-blend record is imported. And all the data is processed from blast hole data to piles. And after that, it takes nearly 1 or 2 months that AI suggest which is the best model we can go ahead. Then after collection of the 2 months data, we go for a deployment of AI, and through that this is based on Python based engine integrations, daily blending recommendations outputs, and quality versus cost models. So nowadays 3 to 4 months it takes. After that we go for a close continuous monitoring, and it took 5 to 6 months. So DCS feed integrations auto update the chemistry of the shift and alert that on what is the best feasible blend scenario we are have. So it is nearly blending cost reduction nearly reduced by 2 to 5%. Kiln feed cost reduced from 10 to 25% in terms of standard deviations, and clinker free lime standard deviations also reduced by 10 to 15%. The blending cost reductions is 2 to 5%, and it is real time update frequency. Now, what is the benefits we are getting? We are getting from the query monitoring and from the long-term monitoring. Each steps we are getting an advantage, from mining engineers to plant peoples to the company management. In the query monitoring, the engineers guess that they have a quick and alternate solutions. They are flexible in operations. There's timely and detailed analysis available, and they avoid the human biasness. The manager, the evaluations of manager has the advantage that they have evaluations of multiple scenarios, elimination of dedicated manpower. They can reduce the manpower which is dedicated. Reduce, cannot eliminate, but we can reduce the manpower, because still we have to do the monitoring. And the company has the good savings, because every saving in the cost of operations in the continuous updation of the inventory. And long terms, we have advantage of the mining engineer is that they have efficient management. He can manage everything. Manager has optimal use of deposits, streamlined query layout, continuous and updations of inventory, and better control over the deposits. Company has the advantage of enhanced money equipments and enhanced deposit life. Here, the main thing is that there is a main coordinations between mines and the plant. Both are understanding each other. The thing is that the mining peoples, it has been predicted that this is the material available to us. So this is the best material we can give. Now, whatever be the things that has to be done, this has to be further modified from to the plant side. Now, plants papers is told, okay, this is the best thing which is coming from the mines we can take. So the understanding between the mines and people reduce a lot of conflicts and give a smooth operations. And this gives the management, top managements, that what decisions has to be taken, and after also the owner also. Here I have the two cost analysis. One cost analysis is from Indian in terms of reserves. So here we have a 6 scenarios in which it is a case of one of the mines in India, in which we have just changes the raw mix, and the reserves is increasing from this 94 million to 500 million tons because of the LSF. In that, what is happening is that I have given this 6 scenario in which plant people tells that some of the scenario is not suitable to me. But okay, we remove that. Then we have this is still another scenario. So whatever be the best scenario you can have achieved. So here we have just first in the scenario we have given LSF 103, silica minus 2.1.95. So we have reserves of only 94 million tons. Then we change in the correctives from in the presence of laterite we give the iron ore. So the reserves has become to 133 million tons. Then again we have informed that okay, we can change this CO LSF 100 to 9, 2.5 and 1.35. Then reserves suddenly increased to 479. Why is it increasing? Because some of the materials which we are rejecting, this is being used, consumed, and optimized. Then again further, I'll go for further modification that if you reduce by 40.92 CO and LSF 103 NAO, then we have a reserves of 431, 531. So it is more. But now what happened is that the plant people telling that we cannot produce a cement of 40.92. Okay, then we can, I am telling you what we require minimum 41%. So we have again carried exercise, and this has given slightly less reserves of 501 million tons. So what is happening is that here is the coordinations between the mines, what we have, and plant, what he can take, is the net result of our assessments. In this, we can also see, I have just calculated, suppose now we know the limestone is going on the basis of auctions. So auctions varies from many, from 300 to 600, based on the location, based on the requirement, based on many parameters. I have taken a sum of the cost, suppose 300 rupees per ton. That means if we save 1 million ton of limestone, from the auction point of view, we can save 30 crore rupees. So in this, we see the reserves is increasing in the second column, third column. Then we have a cost as the rate 300 rupees per ton. Then whatever the reserves, we are seeing the reserves is decreasing. Then what we are seeing, what is the we are comparing scenario one as a base, and what is the impact. And suppose we are using reject handling. Suppose reject handling cost is 75 rupees per ton, assuming. So, and this is being not as used as a reserves, but as a cost reductions. So the last column is showing is that how much we are getting a increase in reserves. The right hand side, we can see, predict this. What is the bar graph showing the saving in the cost? So in the bottom line, we have written is the reserves enhancement with change in raw mix, reducing the stripping ratio due to converting rejects into reserves, resulting into reduction in the mining costs. So this is the cost. This is in terms of our optimization. One more thing is it has been done in the South. One case is in South African case. So by model updations, we have before optimization reserves was 89 million tons, and then life was 30 years when optimizations, and given the best suitable uh, raw mix in consultations with the plant purpose, it has become 2.37. This has not only give the plant setup, because it has also gives them a consistent with the minimum deviation in the quality. And in the right hand side, we have a before optimizations, we have a this OB and the cost per ton in million tons. So in by model validations and scheduling, there is a saving of approximately 2.1 million ton USD per annum just by reducing the rejects. In addition, lies further added to saving over additional 15 years, 16 years. Now, this is the what services we provide is our raw material. Is the geological investigation, recognition survey, geological investigations, CADE, mine planning, and techno-economical feasibility studies. This is the project formations, project implementations, mining equipment procurements, mine development. And then the performance management is the mine resource audits, performance enhancements, remote monitoring, and cost optimizations. What is the USP of our Holtec is that we have a vast global experience. We have a comprehensive project portfolios, hands-on exposure to mining operations, extensive geological database, and unique multidisciplinary domain knowledge. So the rich global consulting experience with 750 more than assignments. And we have a customized mine optimization software. So thank you.